All right, so welcome everybody. I'm very happy to see both our guests online and our guests here today. My name is Mario Romero. I am the Associate Director of Seminars here at Digital Futures. And I'd like to welcome my colleague, Jan Kunwis, who will introduce our speaker today. Thank you.
Thank you for the kind introduction. And there's a bit of an echo, but I will try to ignore it. So I'm really glad to introduce Michel, who is a postdoc currently working on SMART project together with me. And you're currently working at the Department of Mathematics. And we really look forward to your presentation.
Thank you so much. Thanks for joining my seminar. It's an honor to be here and presenting for you. My seminar today is about AI-driven digital twins in action, and my intention is to provide some examples, some use cases of digital twinning in industry and some of the works we have done, and also keep it a little bit fun and informal as much as possible. You see different pictures from the first slide. I will not be able to talk about all of them, but I will handpick some of them. I see a screenshot from a soccer simulation team I was leading when I was in the first year of university and during the high school. It's the first encounter of digital twins that I had, where we basically try to train an agents of players playing in a field and compete with other agents. So it's the first simulation, real simulation that I had experience. And down there you see a quadcopter that we worked in for a competition that we also created a digital twin. We worked with my colleague Edwin, who created it so that we could test different algorithms in a simulated environment so that we can learn from it and then apply it in real world, as well as testing what's the situation of the current robot, the quadcopter, for the competition. And you see my apartment up there, which is a 3D reconstruction that I made for digital twinning purpose, which I will talk a bit more about it. Yeah, and also down there is my test bed that I did a lot of testings during my PhD for optimizing cloud native systems. But I will go ahead and talk about what I'm doing right now. My current project called Smart Predictive Maintenance for the Pharmaceutical Industry. It's a project in collaboration with AstraZeneca and funded by both AstraZeneca and Digital Futures. And it consists of 3 threads. I'm working on machine learning driven optimization and digital twinning in Industry 5.0. We have 2 other threads. One about collecting the data and sensor data and coming up with algorithms for predictive maintenance in industry. And the other thread, which is led by Relani, is here. The other one is with Tian, is about what's the best way to visualize digital twins and present in a best experience, give a best experience possible for the users of the digital twin, together with AR and VR. I will show you some examples of that work. My past project was about profiling network virtualized functions and optimizing their performance for telecom cloud. It was a project sponsored by Ericsson and Boehrer and funded by Knowledge Foundation of Sweden. And during that work, I tried to come up with algorithms and methods based on machine learning to optimize large-scale cloud-native system and create a digital twin of large-scale cloud-native system, and after that, optimize them. And I will talk about some of the work we have done there. But let's start with exactly what is a digital twin. I mean, there is no single definition according to my understanding. And if you read more about digital twins, you will start understanding that different people define it in a different way. And you see here is a humorous memo that I created. Like what society thinks when you say digital twin, some people think of a matrix, but it's a bit far from reality. And you see in industry, different roles may see it differently. Manufacturing engineer may see it maybe as a CAD, or machine learning engineers may see it as a neural network that has been trained. Of course, this is maybe not the case, but I see different people see it differently. But let's understand what is it exactly before we jump into some of the use cases. When you read the literature, you realize that there are many different definitions, and I try to collect a few definitions that made sense to me. One of the very first ones that I managed to find was with Dr. Michael Greaves, which defines digital twins as a set of information constructs that fully describe a potential or actual physical manufacturing product. So it focuses on physical manufacturing products, and in the paper, when you read it, it talks about the real space and the virtual space, and then you can create different instances of that virtual space, and then try to do different hypothesis testing and etc. And it has a connection with the real world. Another definition that I found is from IBM as of 2024, which defines a digital twin as a representation of an object or a system that spans its life cycle, is updated from real-time data, etc. So it adds the systems aspect to the digital twin. You also find this definition from NIH, where defines a digital twin as a digital replica of a living or non-living physical entity, such as manufacturing process, medical device, equipment, or even a person. So it adds the people or living creatures to the definition as well. You see some other, as a virtual replica of an object being system that can be continuously updated, and many more definitions that you can find. When you look at these definitions, and you see that you will see there are a lot of papers, a lot of taxonomies, a lot of literature reviews that goes through characteristics of digital twins. And when you read those, you come up that there are many characteristics that different people, different paper, different companies, organization care when it comes to digital twins. I try to come up with the 5 most important ones, but it's not limited to that. One of the most important ones I realize is synchronization. Basically, many literatures define digital twins needs to be synchronized with reality. And that comes in different levels. It can be either a real-time synchronization, a near real-time, or periodic. But it's important that whether it's not real-time, it should be periodic. One of the main differences with just a simulation is that in simulation, you don't necessarily need to have a connection with reality, but in digital twins, you should necessarily have some connection, whether it's periodic or real-time, but it should be. And also, some may say that the digital twin must necessarily be bidirectional, meaning that a change in digital counterpart needs to be reflected on real one, but it can be also unidirectional, which means only physical, you only see the physical, the digital representation of the physical twin, and there is no two-way connection. Both is possible, and there are different levels. Another very interesting and important aspect is data homogenization, which basically when you have different types of data sources, sensory data, internal system, external system, maybe you get data from an external API, maybe you get data from your own application APIs. Of course, you can look at that information, you can explore that information in an Excel sheet, or you can open it in an application, in, I don't know, Power BI, and you can make a sense of it. But with digital twins gives you this ability to basically present that data into a unified environment. For example, let's give you an example. In industrial setting, when you have sensory data from conveyor belts, you can have the speed, you can have the temperature, you can have the vibration of the motor. Of course, you can get that data into a CSV file and look at it and explore it. But it's very different experience when you have opening a digital twin of your environment and see the data in the context that it should be presented and combine with other data that you get from different data sources. And also when a microservice, for example, send a notification or send a request or wants to do some changes in reality, the digital twin helps you see that change and helps you apply that change in reality. It can done it in different phases, beginning, middle, or end of the life of the environment. Another aspect is traceability, and that traceability comes in different levels. So in digital twin, you should be able to trace what's happening in real system over time when different actions happen, when different states system goes into, and different actors apply the changes in the system. And it's very important, the aspect of digital twins. It doesn't need to be very, very detailed, but it needs to have some traceability so that we can go back in time or action and see what's the effect of your action or states on the real system. And another aspect is analytics, where you should be able to, one of the many important aspects is that you get diagnostics of the current system in both operational level and prediction of the future. And that prediction can be, again, in different level, can be very detailed prediction, very simple prediction, or very advanced prediction. And it can be also prescriptive. It can be prescriptive, meaning that, okay, if something happened, what should we do to mitigate that problem or that action or that situation? And it can be descriptive. Your digital twin can help you also describe what is happening in a humanly understandable ways. And I'll give you some examples in the next few slides. And many more. It's not limited to just these 5. If you look at the literature, I tried to come up with weighted features and try to create a word cloud of all the features that is possible for it to be exist in a digital twin. Some people say simulation capability. Many people actually say simulation is a very important part of digital twins and hypothesis testing. Many people argue that it's not necessarily need to be there, but you see that it's very, very much so many features that you can have in your digital features that digital means that is not necessarily agreed. There's no consensus on all of them among all researchers in this area. I want to get you back to very first digital twin ever proposed or talked about or widely known, which introduced in Apollo 13 mission. Basically, Apollo 13 mission, during this mission, engineers from NASA basically come up with the very first digital twin concept in 1970, where there were no commercial CPU at that time. Actually, the first commercial CPU is introduced in 1971. During this mission is supposed to be a mission of moon landing mission, but it turns out to be a life and death mission, fighting for life and death. Basically, the oxygen tank exploded during the mission, and engineers of NASA tried to come up with a replica of that Apollo 13 spaceship on Earth and simulate the situation on Earth and understand what should the astronauts do in order to survive. And it worked. And that was one of the very dramatic stories I have ever heard about computer science in general. It's very, very interesting. Again, consider that there were no CPU, there were no computational power at that time. And it's been done with a very low resource, computational resources. And this is a part of Apollo 13. I don't know if you saw the movie by Ron Howard. It's a scene that they try some of the parameters on the physical twin of the Apollo 13, and the back there you see the replica on Earth that has been created. Now I want to go through a use case in industry, a few use cases in industry, an industrial application of digital twins. And I want to start by some definition and some information about some of the important aspects of the universal scene description. I want to introduce some of the work, some of the platform. One of the very interesting ones is NVIDIA Omniverse. And I want to also talk about a use case of NVIDIA Omniverse, a digital twinning use case of NVIDIA Omniverse. Very interesting. I thought it can be interesting for the audience. And then after that, I will talk about some of the works we are doing in our projects. So I want to talk about this animation, Brave. I don't know how many people watch this animation. One over there, Mario. 2, maybe. During the production of this animation, Pixar, which is the production company behind the animation, encountered with a problem, with a big problem. And the problem was that the massive amount of data, a massive amount of objects, and things that is in the animation becomes very hard to manage and become problematic to handle. And they come up with this cutting edge or very interesting idea of universal scene description. Basically, when you have a scene in a potential scene that you are working with many different type of file types, that you have OBJ files, CAD files, STL files, PLL files, ADC files, etc. The problem is that when you want to work with all of it and make a change in one of them, it's hard to keep track of those changes in the actual scene that you're working with. So Pixar comes with this idea of universal scene description, where you can combine these objects into a scene using a universal descriptive language. The USD can have a combination of objects, assemblies, lightings, effects, design, layouts, and animation. And I created a little demo. When they introduced this, they come up with a data set called kitchen set. And when you download the kitchen set, you see different folders. And in each folder, you basically have a 3D object of something. This one is like a ball. The other one is a book, for example. It can be a bottle, and you actually can open it and rotate it and play with it. And it can be a bowl. But at the end of this folder, there is a scene file, the USD file, which basically combines all of these objects into a description. And as you see, it's only, I don't know, 200, 300 kilobytes, but it actually have a very too many information in it. Contain so many information, so many scenes, so many objects into one file. An interesting thing is that when you update one of the files, you see that you see the effect in this scene. And you may ask, okay, what is the relation between this and digital twins? That's where the platforms such as NVIDIA Omniverse, which is one of the very interesting platforms, helps take advantage of this kind of file type, as this kind of technology, to provide a collaborative platform that allows building 3D scenes from various file types, from various applications, from different APIs, from different microservices. And basically with tools like Omniverse, you can, when you work with a large organization or in a team where you have multiple people working on the same scene, and you also work with different applications, it can be Maya, it can be, I don't know, AutoCAD, name it, any 3D manipulation, 3D Max. When you make a change into one of the files and you save, it has connectors that your changes applies into reality. But not only that, if you have APIs, if you have microservices that sensory, they comes from the sensory data from the production or from whatever environment that you create digital twins, it applies those changes into the the digital twin that you create. I just try to put some of the examples from YouTube of NVIDIA Omniverse, which shows a very interesting example of use case of digital twins, where they simulated or they created a digital twin of a warehouse of 9,300 square meter. And you see different objects in this digital twin. You can even see the live camera feeds, and then it shows, okay, each camera feed corresponds to what scene in the digital twin. And another interesting aspect of it is you have a 2D view, top view of the production of the warehouse, and it can be used for things like the pathfinding, object detection at different places, and so on. Another interesting aspect is that you can also walk in the digital twin. It's because it's 3D and you can have a VR headset on, or like a game, you can walk in the digital twin. And also another very, very interesting use case they presented in their page is you can ask digital twin using LLMs that what is happening in different aspects. For example, you ask I3D, what's happening in I3, and it shows it has the object detection of what is happening. Some incident happened on that line, and it gives you information of what's happening. And this is just an example of how useful digital twins can be when combined with AI and data-driven information from sensors and etc. During my work with a smart project, the project that I'm involved at the moment, I realized that creating these digital twins, even though very interesting, very powerful, very important, and these tools makes it very easy, makes it easier to make. It's actually very, very time consuming and very hard to maintain. It's very expensive to create such digital twins and keep them updated with every single change, because these are mostly created manually. You have to place the teams together, or semi-automatic at least. We wanted to come up with methods that can automate these steps. And one of the project that is still ongoing, but I have some preliminary results to show, is PerfCam, which is a digital tuning platform for KPI extraction using methods called 3D Gaussian Splatting. And the way it works, we created a little robot, a 3-axis robot with a camera attached on top of it, which you see here. It's called PerfCam. And we place these cameras, a few of these cameras, across a warehouse or across a production environment. And these cameras 24/7 gets pictures of the environment and videos from the environment from different angles, because they can move, they can get different views of the production environment, and combined it with methods such as 3D Gaussian splatting and 3D reconstruction. We basically try to reconstruct the 3D environment such that it can be used in a potential digital twin. That's first aspect of PerfCam. The other aspect is that when you have a lot of sensory data, you have to combine it somehow with the sensory data, because the 3D reconstruction may not be enough. So you get the sensory data such as vibration, sound, vision, temperature, air quality, motion, etc. And you, of course, have to store it in a time series database. You have to label it. You have to use data augmentation. And using methods such as YOLO or convolutional neural network, you get different types of KPIs from the production line. Then PerfCam combines this information into a platform and shows basically a 3D reconstructions with added data on top. And I basically have a test. We tested it on a test production line where we have this augmented data on top of it, which the visualization you see is a work of my colleague Renan here, which basically you see the number of products running in production line, a lot of different parameters that comes with production line. You can walk using a VR headset or just like a game. And you can also see the augmented view, where it's a raw camera feed with added data on top of it, like the products running, number of products, and other statistics. Of course, these pictures are just sample pictures, the ones that will be taken from a test environment, and some of them from simulation. But you get the idea. That's the idea of PerfCam, to extract some of the important KPIs and combine it in a digital tool. The way we calculate the KPIs is basically get the video streams, and we extract the input frames, and using we also have to select the regions that are important for us to extract the data, and combine it with convolutional neural networks. We do classification and product detection, as well as the up detection and the equipment and lights. That's one of the use cases that we hopefully think that it's going to help production teams and quality assurance teams to get better understanding of what's happening on production line, and hopefully using this information, they find the potential bottlenecks, they help them to understand how to optimize the production line, etc. Another use case I would like to talk is in cloud computing. So far, what you see from digital twins are very visual digital twins, like with 3D reconstruction, 3D models, CAD models, etc. But as I mentioned, digital twins can have we can have digital twins in different levels. And in cloud computing, we basically have virtual entity, which are applications, and we want to create a virtual digital twin of that virtual entity. And that's a type of digital twin, but we are basically creating a twin of a virtual object, not a real object. Of course, I saw many digital twins that they try to create a digital twin of a cluster that you could walk in a server room and see servers, their CPU usage, their temperature. I'm not referring to that. I'm referring to what's happening inside the servers and how we can understand, okay, how many applications are running in each server, how we can use that information also to optimize eventually those resource allocations. Allocation of the microservices. So I want to start with some of the definitions of what is a microservice architecture, what is cloud native system, and digital twinning for optimizing large scale cloud native system, and talk about some of the works we have done in this area. So let's start with microservice architecture. And what is a microservice chain? Microservice chain basically when you have a source and you want to send a request from a source to a destination. One thing that happens very often in cloud system is that it goes through a bunch of middle systems, we call them microservices, which these microservices are supposed to be completely independent from each other. They have to be loosely coupled, and we should be able to deploy them independently in different hosts without any dependency to each other. And the goal of this is that different teams actually can work in different microservices and come up with their own APIs. That's one of the advantage of microservices, but I'm not going into that. But that's the idea. And there are many examples of microservice chains, firewalls, load balancers, gateways, CDNs, etc. And the reason that I mentioned those because my PhD was about virtual network functions. But in order to give examples that you may heard, we can think of a machine learning pipeline or a workflow as a microservice chain, where you have different containers. Each container does one job, and the result of that job goes to the next one. That's one example of or any type of workflow. Or maybe it can be a website. You open a website, you have a website or a web page, and that in order to populate that website, you have to call different services, get different information from different sources, and then combine them to show a website, for example. That's a type of microservice chain. Even though it's a very interesting concept, but it makes a problem. And the problem is that over time, when the organization gets larger, the number of employees increases, the number of microservices also increases. And managing these microservices is a very big challenge. Actually, what you see is so-called Death Star architecture, where we are dealing with a lot of interconnected microservices, which is very challenging to handle, sometimes even a nightmare. And I also put a picture of the black hole in the center of our galaxy. I don't know if you can realize any connection between these and that. If you can, then you're on the same page. If you don't, basically what I mean is that when you're dealing with a lot of microservices, it feels like you are working with a black hole. Like it's very hard to manage and sucks you into keep maintaining the things that you always curse the people who work with architecture. I heard that a lot. And maybe you say, okay, this picture from Netflix is taken from a talk with Netflix people and in November 2014. The other one, Amazon. That picture is shown in one of the talks in 2008. And the other one from 2013. And you may say, okay, maybe this problem is solved nowadays. Maybe we don't have this problem anymore, this explosion of microservices. Maybe they solved it. And then I was listening to Amazon reInvent last year, and the CTO was explaining the number of microservices at Amazon as of 2023. And you see the number of microservices actually, I don't see that it decreases. The complexity seems like is increasing, especially with advent of large language models, where it helps you generate the codes, and a lot of times microservices, you see the number of microservices increases. So it's a complexity. And during the talk, you see they presented that there, I don't know if it's visible, but there are some yellow lines that shows, okay, if you open Amazon.com, that's the number of microservices being called to populate the page for you. So you see there's a lot of complexities there. Of course, there should be some, I'm sure there are caching layers that every time it's being called, but you know what I mean. Around, I guess, 2012 or 15, I don't recall, but around that time, prominent players in the field realized that, okay, managing this number of microservices is going to be a problem. And they started a Cloud Native Foundation where it's a set of, they encourage or introduce set of technologies that empower organization to build and run scalable applications in modern environments. And they encourage people to use things like approaches such as using containers, service meshes, microservices, as I mentioned, declarative APIs, and immutable infrastructure. And the idea is that these techniques are supposed to enable organization to build loosely coupled systems that are resilient, manageable, and observable. And I want to emphasize on the observability and manageability. You know, when you're dealing with so many microservices and services in your system, it's very hard to keep track of them, connect them, their IP addresses, their location, their resources they use, what they are doing, do they need scale up or scale down, etc. So they come up with platforms, and one of the most de facto platforms is Kubernetes, which is mostly baked by Google, which helps you basically manage these cloud systems, these microservices in a more easier way. And it helps you have very good observability of what's happening on a large cloud system. And there's a problem when you're working with large number of microservice chains. There are questions that organizations or providers need to answer from the performance perspective. And one of the first ones is that, okay, I have this many microservices and I want to deploy it in a given cluster. What kind of resources should I have? How to allocate resources to each microservice? In other words, how many CPUs, memory, disk, network, GPU, etc. I have to allocate to each of these microservices? How many replicas should I have? Second question is that how to place them in a given cluster. Which one should I place them next to each other? The ones that talk a lot together. Okay, which one are they? It's hard to find manually. And the goal is to maximize the performance, in other words, minimize latency and minimize the cost. So with the least cost, you get the best performance that you can get. And that's an interesting optimization problem that many papers and many researchers work on. So when you want to answer those questions, you can't do that without looking into the dynamics of each application. So you have to understand that each microservice on its own use a specific amount of CPU when it's being called. So they have different CPU demands, different memory demands. They write on the disk differently from each other. They talk to each other differently, and they maybe send information in different ways. And some of them use GPUs, some of them don't use GPUs, and any other resource may affect performance. And in order to really model the application, the system, you have to understand all of this in order to do that. And there are many ways to model a microservice when you read the literature. There are complex system analysis ways. There are machine learning based ways, like using regression models, classification, decision trees, neural networks. There are statistical analysis works that does correlation calculation in order to find the bottlenecks, what if analysis, hypothesis testing, etc. The thing is, you cannot understand the performance of an application in isolation. You have to put it into context. When the application is deployed on a host, then what's going to be the performance? You can't just look at the application, okay, what's the performance of this application? You have to understand that the application behaves differently in different hardwares. So you have to also consider the hardware aspect, like what kind of hardwares you have, what's the brand of those CPUs, what's the speed, Well, how many cores each CPU has, memory, bandwidth of the memory, the bus, the network, the speed of the storage that you have, its lifetime as well, GPU and other resources. Basically, when you have a cluster, you have a bunch of hosts, and when you want to deploy a microservice, a single microservice in this large cluster, you don't usually deploy one instance of that microservice into one host. Why? Because maybe that host exceeds maybe the traffic increases and that host cannot handle that many requests. So you need to have multiple replicas deployed across a cluster, and a load balancer need to balance the load between the replicas when a microservice is being called. Another aspect is that you don't have only one microservice. As I said, if you have a microservice chain where you have many different types of microservice, and each microservice, which I showed with the color, have many replicas. And when I say microservice, it doesn't mean that a microservice can only do one thing. A microservice may have multiple endpoint functions, and each function on its own can do a separate thing. For example, let's imagine we have a microservice of a university application, university microservice, let's say, university management, students management. That microservice may have an endpoint for calculating how many courses each student has. Another microservice, another endpoint of that microservice may calculate the, the average score that student has, etc. So different endpoints that the microservice can have. And each endpoint then is being called, or endpoint function is being called, may invoke or spawn one or more than one threads. And each thread that is being run is using different amount of instructions. Each instruction runs different cycles. That thread may access the memory in a different way than the other endpoint function, and read and write in the hard drive differently. So it gets even more complex when you consider these aspects. You also have a load balancer. There are different load balancers behave differently. There are many different algorithms of load balancing, and that also affects the journey that the request has. For example, in a case where we have a microservice chain of green to the blue to the red to the yellow, different people who wants to call this microservice chain may experience, not they may experience, but their journey of calling different replicas may be different. For example, the first time they call this microservice chain can go through this path, still green, blue, red, yellow. The second time can go through this path, and the third time can go through this path, because of the load balancer balance them differently based on different algorithms. And as you can see, this is another aspect of complexity. So in order to efficiently create a digital twin of the cloud system, where not only show what's happening, but also simulate or predict what's going to happen in a specific scenario, you have to consider all these parameters, all these aspects of complexity in your system. And that's where we introduced two works. One was PerfSim, a performance simulator for cloud-native microservice chains. You can access it through perfsim.com if you want. The second is a method for optimizing the system using reinforcement learning, graph attention network, and DQN. And that uses basically the PerfSim. With PerfSim, you create a digital twin of the system, and then from there, you try to optimize the system using a reinforcement learning approach. I'll very quickly go through the PerfSim. How does it help simulate different scenarios, and how does it create the digital twins? Basically, with PerfSim, you deploy each microservice, we isolate each microservice into a host. And in that host, we start stress testing each endpoint of that microservice. And by stress testing, we can extract many different information, many different models. The first model is that how does this microservice call other microservices? Let's not use my word microservice. How does each endpoint function of this microservice calls other endpoint function of itself or other microservices. So we create the service chain model prototypes, which we use things like Istio for understanding service mesh and etc. And performance traces, we also collect performance traces, like how much CPU usage they have, how many times they allocate, they call the CPU cache, how many times they read and write from the disk, and etc. So we create endpoint function model prototype. We also get information from the host. Platforms like Kubernetes allows us to get that information very precisely, like how many CPUs each host has, what's the speed, the model, etc. And we can create the model prototypes. We also do the same with the network. So we stress test using iPerf and other tools to understand the bandwidth of network and the connection between network and the link delay, and then connection between the routers. And we create network topology prototype of that. Combine it with the user-defined scenarios where user basically wants to simulate its own scenario. Let's say user wants to see if in this state of the environment, if they increase CPU for a specific microservice, what's going to happen? How it's going to affect the performance? How it's going to affect the cost? So it come up with its own user-defined scenario, whatever it is, based on resource allocation, based on placement, whatever. And that can be done through a JSON file or through a dynamic control object in Python, and you run the simulation. And perfsim basically simulate that scenario and give you information such as response time per service chain, response time per request, average CPU time per service, average memory, etc. So we created perfsim in order to understand different scenarios and test different hypotheses, not only for people to test for themselves, but also in order to be used in optimization problems, in solving optimization problems, where in an optimization problem, we basically need to test many different scenarios, many different parameters, and see if the system gets optimized, gets better, or gets worse. And that's the main motivation behind perfsim, to create something fast that can simulate and give us a result based on different scenarios. And in order to just quickly go through different layers of a microservice-based cloud-native system, and it's a repetition of what I already said, we have infrastructure level, cluster management level, control plane, data plane, and application level, usually in a cloud system. Of course, in data plane level, we have services that are microservices that I already explained. And in application level, we have endpoint function. So each service has one or more than one endpoint function. And of course, we have service chains, C1, C2, C3, which form a chain of microservices. And infrastructure level, we have a bunch of hosts and a bunch of routers that connect these hosts. And as I said, each service can have one or more than one replica to load balance between various hosts. We come up with this paper, Graph Attention Network for Deep and DQM for Service Mesh Optimization. It basically tried to create a digital twin of this environment, and we try to train an agent that agent needs to learn what action needs to take in order to increase the performance of a cloud system in a given state. And in order to do that, we need to somehow explain the state, and that's where we use perfsim, and we use this graph representation of our environment. We basically turn the system, the environment, into a graph, and in this graph, each node has a different type, and each edge also have a different type as well as parameters. And basically perfsim tries to generate different set of simulation scenarios with different arrival rate and different batch sizes for each microservice chain. And it basically first of all creates the representation graph from perfsim, and using a technique called representation learning, we try to learn a representation from the environment, from the graph that perfsim creates in each step. And we we provide that representation as an input for our DQ, and together with the reward of that representation, and find out what's the best action we have to take in order to improve the performance. And in this study, we only consider a CPU increase, decrease, and we also considered affinity and anti-affinity policies. And we also evaluated the results of this study. This is for perfsing. We evaluated it using 104 scenarios. We've understood the more threads you have, the more chaotic the system becomes, and the slower the perfsing becomes, and the less accurate the system becomes. But for scenarios that we have stable state of the system, the threads are running, the CPU usage is not too high, it can simulate very accurately. I have ideas to make this much more accurate in the future, but at the moment I'm not working, but I have to come back to this and make it even more accurate. We also calculated the speed of execution, which is hundreds of times faster than you run it in real scenario. Basically, you can simulate a cluster of hundreds of nodes, actually 100 nodes to be precise, in a single laptop, and it's 10 times, 100 times faster to run that scenario in your laptop rather than in reality. And it's also much faster, and it's good for researchers also to use. We also tried the data star architecture to see if it's possible to simulate that, and publish the results as well. We also evaluated the optimization paper using a very limited number of testbed hosts, and we find out that even though the method increased the cost, it's come up with much more costly method to improve the performance, but it actually improved the performance in many scenarios. More evaluation can be done, and this method can be improved. But I believe that this is going to be a very interesting topic to continue work on. And thank you for listening.